some people don't really like having music on. I do. I mean, I like work so much better with music on.
Since you do videos, like you should definitely have an opening theme song.
Yeah.
Right before you start giving notes, like it's very inviting.
Scientifically, music helps as long as it's within a certain range. If it's too loud, it becomes like super distracting. And if it is too quiet, it's also super distracting. But if you're like somewhere right in the middle, it actually improves your performance.
Interesting. Yeah. I find that with like.
I just hated being quiet. I don't like it quiet. I was up tonight, so I really hate it.
Yeah, my wife likes to study with or read with like the TV on. I can't do that.
I can't do that.
But music is like yes, but she like can't do music, so I don't know. We just stay in different rooms.
I was gonna say study in the room.
All right.
I like science, and I like science more for the fact that
Yeah, I know, right?
science, studying science seems like you're moving into science.
Yeah. Just depends. I gotta mix it up. All right. Energy, power, and you guessed it, lumping. Yeah, I know that seemed like the next logical thing after energy and power. By the way, I just finished this really great book that is mostly it's about power by Michel Foucault. It's called The History or A History of Sexuality, Volume 1. Really good. It's like you might think it's about sex, but it's actually about power. Interesting book. Topical too, right? So the law of conservation of energy states that for an isolated system, the total energy remains constant. Okay. Let E be a function of time, representing the total energy in a system, and power be a function of time representing power into a system, defined as the time rate of change of the energy in the system. Okay. The energy in a system can change if it exchanges energy with its environment. We consider this exchange to occur through a finite number of ports, each of which supplies or removes energy, positive or negative power, as in figure 1.2, which is right here. So, system, as usual, it's a peanut shape. And we have a finite number of ports. I had to choose a number, 3, but there could be more, right? Or there could be fewer. So through a port, we can have power come into a system. Notice I'm always drawing the arrow in because power into a system is considered to be positive. Power out is negative. So if we draw the arrows in, then it comes out negative. We know it's leaving the system. Okay. This is expressed in an equation for power into a port Pi and N ports as the power being equal to the sum from I equals 1 to N of the port powers. So you sum up the powers into each port and you get the total power, which makes sense, right?
Is there a reason you use script P?
Yeah, it's just like, I don't know, common to use script P for power. I try to stay kind of close to the notation in the Rowell and Wormley textbook for this. We construct our systems such that they have no internal energy sources. By saying that, I don't mean like we're like, oh, well, we just won't build systems that have internal energy sources. What I mean is we're never going to include the sources or the power sources inside the system.
The sources is coming from outside. So like if you have a battery in a car, the battery is on the outside of the car, powering into.
Yeah, so we consider the system to be that which does not contain the battery. Yeah. All right, so lumping. We already to lumping. We already did energy. We already did power. We're already lumping. presidents of the United States wrote a fun song about this. So, we have assumed power enters a system via a finite number of ports. Similarly, we assume energy in a system is stored in a finite number, m, of distinct elements with energy EI, each of them having energy EI, such that if you sum up all of the energies in each element, you get the total energy in the system. We call these elements energy storage elements. So we'll talk more about energy storage elements. But we're familiar with the capacitor, for instance. Capacitor stores energy in an electronic system. So that would be a lumped parameter element in an electronic system that stores energy. Mechanical system, you might use a spring, for instance, to store energy. So we'll talk more about that later today. In fact, this very day, we'll talk about it. Considering a system to have a finite number of elements, as we have done, requires a specific kind of abstraction from real systems. A familiar example is the point mass of elementary mechanics. And when I said point mass earlier, everybody looked at me with like blank stares, and I was like, is this not a thing that you guys have heard before? So you guys have definitely used point masses before. You just might not have heard them called point masses. So, in your physics class, when you were like, oh, hey, kinematic equations / summing forces on a, oh, you might have called it a particle, that maybe you launch and you do some nice, what do they call those problems?
Force diagrams?
No.
Instead of thinking of the mass as like a big block, having
Yes.
distributed force, it's one little teeny,
Just the point.
extremely dense atom.
Projectile motion. You guys used this. So when you're out there, if you took physics here, and you're out there in the what do we call this? The quad? You should call it the quad. There are 4 sides to it, right? Okay. So the quad. And you're on the quad, and you're launching those rockets. Remember? I mean, I've never taken the class. You guys took the class. You stand there and you pump up. I mean, I've seen it like I've always like am tempted to walk through it, but then I'm like,
He did say
I don't
want to
mess up the science.
People, so you should
Really?
just do it. And give
Okay.
credit.
Just like run away. Yeah. Anyways, so launching those rockets, you guys, I am very confident, wrote some equations to like maybe like predict like what the initial velocity was or something. You guys calculated something, and that corresponded more or less to the experiment, depending on the conditions, right? So you're really familiar with this. I mean, you've done it. That's mostly what you've done. You did a little bit of rigid body motion in dynamics class, right? Mm-hmm. But before that, everything that you had seen, as far as mechanics goes, was considering things to be point masses. Okay. So this is a sort of abstraction that we use a lot. We say, and not just for masses. We say it interacts with its environment via specific connections called ports. So for instance, for a point mass, maybe it's attached to a spring element. So we would say that like the spring connects to the point mass through a port. And behaves a certain way in these interactions. So for a point mass, it would be Newton's second law, right? That would be how it behaves. F equals ma, that good stuff. We do not often encounter an object that behaves as if it has mass but no volume. I mean, I don't know about you guys. I don't often encounter these things. So something that has mass but no volume, it's not something that we really encounter. However, it's a useful abstraction for many problems. Okay, so we use it even though they don't really exist, right? We're just like, if you take a point mass and then like actually it was a rocket, right, that you guys used, but like surely it's not actually a point mass, but you used the equations and it kind of worked, right?
Mm-hmm.
When we abstract like this, considering an object to be described fully as a discrete object with interaction ports, we are said to be lumped parameter modeling. Okay? This is often contrasted with distributed or continuous modeling, which consider the elements in greater detail. For instance, an object might be considered to be distributed through space and perhaps be flexible or behave as a fluid. So that would be a distributed model. Whereas the perspective we're going to take in this class is going to be a lumped parameter modeling approach. Determining if lumped parameter modeling is proper for a given system is dependent on the type of insight one wants to achieve about the system. The system itself does not prescribe the proper modeling technique, but the desired understanding does. Every system is incredibly complex in its behavior if one considers it as a fine or at a fine granularity. So, I mean, even like a circuit, which is like a really well-controlled system that's like, we've done a really good job of making electronic components that are like really, function as they're supposed to function, right? But every one of them has some variation. There are electrons wanging around in there. Things heat up a little bit. Like, even when we consider a circuit that is a really high quality circuit, it's always some abstraction that we use for the model. In this light, it is striking that a simple model works at all, right? I mean, it's like there's no reason a priori to expect that it would. Like, it's like we wrote down some equations and we were like, see if this works, guys, and it ended up working, which is like, that's cool. But there's no reason beforehand to expect that a simple model would work. Maybe the world could be such that it's every interaction is so complex that you can't write down a simple equation that approximates it. But it turns out the world mostly can be modeled with simpler abstractions, which is pretty cool.
Depends on how close you want to get.
Yes, exactly. Which is the perspective we're taking is it depends on what you're interested to know. So, it's surprising that it works at all. Nevertheless, it's highly effective. Lumping is highly effective for many analyses. It is important to note that lumped parameter models can be applied at different levels of granularity for the same system. Finite element modeling, also called like FEA analysis, programs, commercial software like ANSYS uses this, can use a large number of small lumped parameter model elements to approximate a continuous model. So it can chop a continuous model up into a bunch of little discrete chunks, and then treat it as a sort of lumped parameter model. Such applications are beyond the scope of this course. In the system dynamics course, we'll just like barely touch on that. We'll talk a little bit about how you can do so for instance, a course you'll take in your senior year is heat transfer, right? In heat transfer, you're interested in how thermal energy moves around through materials, via conduction, convection, radiation, etc. And it turns out that one really useful thing to do with thermal models is to chop them up into small pieces and do numerical simulations on what would happen, especially when you get into very complex geometries, because your analytic solutions to the equations are going to be less and less helpful. So we'll do a little bit of that in system dynamics as well. And what you could think of is like you're trying to decide between these, and one example would be like, say you have a pipe. I'm going to make it a little bigger. So you have a pipe. You have fluid flowing through this pipe. Now, you might care about what the actual velocity profile looks like in this. So like if you took a section of it and you looked at the velocity profile, you would find, next semester in your fluids class, you'll find that the velocity at the outer diameter, or out the outer radius, is pretty small. And we actually often approximate it to be 0. But then as you go towards the center of the pipe, you find that the velocity increases more and more. So there's this profile, this velocity profile. So it's not like all the water is moving through the pipe uniformly. There's stuff at the edges is moving slower than the stuff at the middle.
Mm-hmm.
And sorry?
Like an Insisius, how the wire kind of.
Yeah. The different phenomena, but yeah, it's so you can think of this as like in here moving fast, up here moving slow. Now, you might care about that. Like so, for instance, you might have like you're maybe designing a valve that's like going to come down and like shut this off or something. Who knows? Maybe you're designing, and then you can't retract it all the way. It's got to stick out a little bit. And when you retract the valve up, say you want to impede this as little as possible, or you want to have you're interested to know what the shape of this, how the shape of that affects the flow of the fluid. So you could think of the streamlines as going around it, and you might think about what the geometry is going to affect how the fluid moves around it. And you might want to gain insight into that by looking at how the fluid flows around it. In that case, you need like a distributed model. You probably are going to need computational fluid dynamics software. ANSYS also includes that. And you're going to want to look at like a simulation of this stuff. Okay? But maybe this pipe is being used like this. You've got a tank here, and maybe there's like some water coming into the tank, and then maybe it goes through this and then it comes out here. Maybe you've got another tank down here, etc. A system with a bunch of maybe tanks and pipes. Maybe there's a pump on here also. So there's a pump on here that's like increasing the pressure between these 2 points. And maybe what you care about is maybe controlling the level of water in here, given like a variable input flow here. Maybe it's like runoff water or something, and so you can't control how much comes in here, but you can change the pump flow rate or the pressure or whatever on the pump. And so maybe you want to have a constant volume in this other tank. That sort of problem is really good to solve with a lumped parameter model, okay? Where you say, okay, this tank, well, it's got, yes, every point in the tank, if you think of it as a distributed system, every point in the tank has a pressure. So if we said x, y, so pressure is a function of x, function of y, and a function of time. It's complicated as hell, right? It's like every element you got to keep track of, and there's a lot going on there. Yeah, and like the flow through this orifice is going to be, something that's really complex through the pump, and then it comes out. I mean, there's all kinds of stuff going on there. And sometimes you care about that level of analysis, but other times you're just like, I want to control this, or I want to simulate how well I can control this. And so you're going to take the position that, okay, this tank behaves like, and we'll talk more about this next semester in system dynamics, but this tank behaves like a fluid capacitor. It contains a certain amount of fluid, and its pressure at this point kind of describes it in a lot of ways, like the height of the water in it, or the height of the fluid in it determines what the pressure is there, and maybe like the velocity of the fluid leaving the tank through the pipe. That's another parameter. That's another variable that is important. Maybe we could say those two kind of govern it, and then there's a relationship between the two, and we can develop elemental equations for it. Similarly, you could say the pipe maybe has like a fluid resistance associated with it, where the pressure will drop across it. So there are these sort of analogies to electronic systems that we could develop. But the main idea, though, is that we could just look at this at sort of a high level and lump these things. Say, okay, the pipe acts like a fluid resistance, where there's a pressure drop across it, there's a velocity, or it's a flow rate, right? A flow rate of the fluid in, flow rate of the fluid out, and that's what we're going to treat this pipe as. We don't really care what the velocity profile is for that kind of analysis. We just care about like how much flow is going to come out this end and what the pressure drop is across it. So lumped parameter modeling can be really, really powerful and really, really useful and apply to lots of different types of systems. And I actually am a little biased, but I feel like it's more useful as a tool to calculate stuff than a lot of the distributed models are. So like you're going to learn in your fluids class some distributed modeling techniques for fluids. You learn in your heat transfer class for thermal systems and stuff. And those are really great, and they really give you a lot of intuition about like this kind of stuff. But when it comes down to calculating something, oftentimes lumped parameter stuff is going to get you what you want to know faster, or maybe at all. One example would be, say you're like, okay, so an example of when you would be really informed by a distributed model, and yet the distributed model would be not useful necessarily for calculation, but you might say, okay, just the insight that I gained from it's important. Like you might want to be able to measure what the flow rate is through this. And so you might stick a probe up here to measure the flow rate. But if you don't know that the velocity profile changes, the flow rate profile changes in the pipe, then you're going to get a reading and you're going to just think, oh, well, that's the velocity. But if you know that there's a profile that develops, then you won't be taken in by that sort of naive assumption. Okay, that was all I've got for that lecture. Any questions on that before we move on? Yeah.
Does the electron is it like the fluids? There's laminar motion or an ideal motion, or just we don't care about that?
Did you say laminar motion, like with fluids? So is in lumped parameter modeling, do we consider that? Is that what you're asking? So we typically don't. So in this example, like the velocity profile, I mean, that's assuming that you're going to have laminar flow, not turbulent flow. But you might have turbulent flow, and especially like when it goes through a pump, you're going to have turbulent flow happening, right? And that's very complex, right? There's a whole lot going on in there. But from a sort of system dynamics lumped parameter modeling perspective, we can just ignore all of that going on, and we can say a pump behaves like a pressure increase, or maybe a flow rate increase. And we can then sort of, I guess you could say, like, tuck all the details in, right? Like, just say, yes, I mean, there's turbulent flow going on in there. There's a lot happening. If you wanted to design the pump, you would need to explore that, right? But if you are just using the pump in your system and you're designing the whole system, lumped parameter modeling is a nice way to go, and you can avoid those questions of laminar versus turbulent flow, effects of the detailed geometry of the pump. You could look at just like what the pump curve looks like, and then just extrapolate from that and build a model. These are always approximations, right? But they're typically really useful approximations. So, not always. And sometimes you might want to do a lumped parameter analysis and learn that you really need the distributed analysis. So, yeah. Okay. Cool. Any other questions?